All right. The question was entropies are calculated from heat capacities. Yes, but they aren't directly determined from heat capacities. So, for example, water has a very high heat capacity, correct?
Yeah.
4.18. Is it? Yeah.
Yeah.
Steam has a much lower heat capacity, like half of it, 2 point something, right? And so does that mean since steam has a lower heat capacity, that steam has a lower entropy than water? No, because entropy is determined from the heat capacity versus temperature curve by taking the area under the heat capacity versus temperature. In other words, it's something called an integral. It's an integral of the heat capacity at a given temperature. All right, other questions from 0 to whatever temperature you are looking at? Oh, go ahead, Matthew.
If molecules with more atoms tend to have higher entropy, what about single atoms, like if they're like large? Do they?
All right. There's the question is, bigger molecules with more atoms do have higher entropy, right? What about bigger atoms versus smaller atoms? Would bigger atoms have higher entropy than smaller atoms? And so if you're looking at the atom itself, no, because the atom would be like in a certain position. Now, if you're looking at an atom within a volume, maybe the smaller because you could position it in more places. But if you're thinking about the electrons, electrons are very tricky things because can electrons really be pinpointed? No, electrons aren't really particles because when we're thinking about positional entropy, then that depends on the position and the different positions it can have. Well, in one sense, electrons can have a position. You can pinpoint it, but because of the Heisenberg uncertainty rule, you lose information about its energy. And so the electrons, when we say at 0 Kelvin, that's absolute zero because what happened at 0 Kelvin? All motion stops. But do the electrons stop moving? Or are the electrons just there? It's hard to describe an electron. Are electrons like little particles in a gas or in a vacuum? No. Are electrons waves? No. And so they're neither particles nor waves, so they're very difficult to describe. But anyway, there's going to be energy called the zero-point energy. Have you heard of the zero-point energy? Zero-point energy is something maybe from Chem 1A, the quantum chapter. When you hit absolute zero, the atoms and molecules stop moving, but the electrons cannot. Because the electrons are always going to have that energy, even at 0 Kelvin. And so for single atoms, this is the single atom in one place is just one, and so it doesn't matter how big or small it is. It's just one possible position. And then if you have more places, then you can have more positions. All right, other questions? Boy. Yes. It's hot in here. When it's hot like this, it's hard to
Take the test beat over.
talk. It's hard to lecture. It's exhausting.
Take the test and let
Take the test and let
it go.
you go. But since we can't, unfortunately, we can't lose that time. So let me talk about electrolytic cells. So we were looking at this cell quite a lot, the zinc copper cell. Some kind of salt bridge in here. the electrons naturally want to flow which direction? The electrons are going to flow left to right, from the electrode to the anode to the cathode. Well, we can force the electrons backwards. The way we force the electrons backwards is we just hook up a power supply or a higher voltage battery. And so let's look at a power supply here. On the power supply, you can monitor two things. There's usually a knob here. You can adjust the voltage. And then on some power supplies, you can adjust the amps here as well. What we're going to do is, for electrolysis, we just adjust the voltage. We apply enough voltage so that this becomes increasingly positive. The more positive this becomes, the higher the voltage, the more negative this becomes here. And so we just crank up the voltage until this is so positive, it's going to oxidize something, right? And the electrons flow this way. And so we have oxidation occur here. And so in other words, we're going to oxidize the species with the highest oxidation potential. It doesn't have to be under standard conditions. Oxidize the species with the highest oxidation potential, whatever that is. And so we look at all the species in contact, including the electrode, and see what's going to be oxidized. In this case, the species with the highest oxidation potential should be the copper metal, but not always. And then over here, we are going to force the electrons out. And so over here, we reduce the species with the highest reduction potential. And so that's how that's going to work. And so when we recharge a battery, what terminal do we hook this up? We hook the positive to what terminal on the battery? The power supply positive terminal goes to the positive terminal of the battery or the negative terminal of the battery? It's going to go to the positive terminal of the original battery. But when we turn up the voltage, and the volts that we got to hit here, this has got to be greater than 1.1 volts because of the overpotential. The overpotential, sometimes we have to overcome a little activation hump to get it to go. And so we need greater than 1.1 volts. Those electrons are naturally trying to flow to the cathode with 1.1 volts, so to reverse this, we got to go greater, right? Now, when we start to recharge this battery, is recharging, then what we do is, this was originally the cathode, right? And this is going to the cathode of this. It was originally the cathode. Because when we start to recharge it, is it still the cathode? Because, what's always the same? Reduction always occurs at the cathode, no matter if it's electrochemical, voltaic cell or a electrolytic cell. It doesn't matter. Any electrochemical cell, the cathode is where reduction takes place, and the anode is where oxidation takes place. And so when the battery is recharging, what happens? This electrode no longer becomes the cathode. This electrode is now the anode. And so when battery is recharging, then this becomes the anode. And the anode supplies the electrons, right? And so this is what we do. We just swap it. Originally it was the cathode, now it's going to be the anode. Over here, this was originally the anode. And now when we're recharging it, it's going to turn into the cathode. And so we have the black lead over here, and then the red lead goes over here. The red lead would go to the red terminal of the battery. The red terminal, when it's recharging, becomes the black terminal, which is the anode. Does that make sense? And so all we're doing is, so as we're reversing the reaction, we got to reverse what they are. But the battery, the battery does the positive. The positive is usually printed on there or permanently marked on the battery. So you're not going to be erasing the positive and writing a negative there, right? It's going to stay positive. And so it's kind of weird because you put the positive terminal on the positive, but really, when we're doing this, the positive is going to go through the negative once you turn the voltage on. That's recharging a battery, but we could also do other things. We can make reactive chemicals using electrolysis. And so let's do that here. And so the amps, this is important for stoichiometry. Actually, let's talk about the amps here. We'll leave it. We use the amps in stoichiometry calculations. So let's say this battery was recharged for 5 minutes at 100 milliamps at a voltage. Let's see. Let's do 2 volts. And so what we're trying to do is we'll see how much zinc solid was plated on the electrode. This amps can be either. This is for any cell. It doesn't have to be an electrolytic cell. A voltaic cell is fine too. If we have a voltaic cell and we're measuring the current, the amps is called the current. When we're measuring the amperage, then we can determine the stoichiometry of what's happening there. Because do you know what amps measures? Amps measures coulombs per second. How many coulombs of charge pass by per second? 1 amp is defined as 1 coulomb of charge per second. An electron has 10 to the minus 19 coulombs. And so if 1 coulomb of charge passes in 1 second, that's a heck of a lot of electrons, right? That just pass by. And so let's go ahead and do this. This is just your stoichiometry, and so we need some starting point. And so the thing that's fixed is 5 minutes. And if we know the amps are coulombs per second, then we want to go from minutes to seconds, so 60 seconds per minute. And then 100 milliamps would be 0.100 coulombs per second. This is 100 milliamps. So the second scale. Now we have coulombs. And so we could do the individual charge on an electron, or we could do the charge on a mole of electrons. The individual charges on an electron is like 10 to the minus 19 coulombs per electron. A mole of electron has how much charge? Well, this one is a little easier to remember because you might have used it recently. And that would be 1 mole of electrons contains 96,485 coulombs. What do we call this constant? The Faraday. That gives us moles of electrons. And then from stoichiometry, we know that to plate zinc, every zinc ion has to get 2 moles of electrons, and then, a mole of zinc ion, plus 2 moles of electrons will yield a mole of zinc solid. And so it's a 1-to-1 or 2-to-2. Is it? No, it's a 1-to-2 ratio. So 2 moles of electrons for every 1 mole of zinc solid precipitates. And then let's get the molar mass of zinc. 6539. 65.39 grams of zinc per mole of zinc. So everything cancels. That tells us how many grams of zinc will precipitate or plate on the electrode. When the zinc plates out on the electrode, oftentimes it might not look as nice and clean, because it all deals with nucleation and growth, right? A lot of metals are microcrystalline. The crystal is extremely small. If you get big crystals, then you'll see it. Like, for example, when you were plating out the copper, just in the electrochemical cell, it didn't form that smooth surface. It formed a fuzzy surface, right? That fuzzy surface is due to these little tiny copper crystals that are growing out from the electrode. And so normally if you want nice smooth, you want to do the opposite of what we're doing with this crystals lab. What we're doing with the crystals lab, we're trying to grow nice big crystals, right? But for plating metals out, you want to do it nice and nice and small, tiny crystals. The tinier the crystals, the less jagged, the appearance of the electrode is going to be. And so you want lots and lots of tiny crystals. Well, how do you get lots and lots of tiny crystals? Well, one way of controlling this is this. You probably wouldn't want to plate zinc. What would you want to plate zinc onto? Well, maybe iron. We'd want to plate some zinc onto iron, but a lot of the iron isn't plated electrolytically with it. Zinc has such a low melting point. You know what they do? They just take a whole bunch of molten zinc and just dip your parts in there, rather than plating it, right? Just dip it. But other people like to plate like gold on, plate thin film of gold or copper on other metals. You could do that, But normally what you do is you start off with very low concentrations. So let's say you want to plate copper and you want a nice smooth coating of copper on the electrode. Then one thing, you do very low concentrations, and those very low concentrations help, slow down things, rather than getting rapid crystal growth out. This. Now, and make things a lot cleaner. But if you use very low concentrations, then it's rapidly depleted. Right? You could use low currents rather than milliamps, maybe microamp currents, something like that. But it's rapidly. But there's one way to control the population of free copper 2 ions. One of the ways is they get a whole bunch of copper and then complex it with ammonia. And when it's complexed with ammonia, you have a very low copper 2 ion concentration in there, free copper 2. But as that copper 2 is being depleted by plating out, more is being regenerated by a Le Chatelier shift, right? And so it works out nicely. that you have this source and the free copper 2 ion can't get too high because of that. Does that make sense? And so in other words, if we just use a tiny concentration of copper 2, then you're always refilling it. But if we complex the copper 2 with ammonia, then here's a good way of keeping the concentration very low and not having to refill it all the time. And that is just do Le Chatelier's. As the copper 2 is being plated out, more is being regenerated. Le Chatelier's shift. This way. Well, here we're just plating out some zinc. And, plating out zinc on zinc, which is fine. But maybe if you could get one of those, you see one of those electrodes I saw was nicely plated with copper, right? So you could get a graphite and then just coat it with gold, or something like that. Gold ions are hard to get in water, but if you complex them, yeah, then you can. Right, electrolytic cells can be used to generate chemicals and quite reactive. One of the electrolytic cells we were talking about yesterday was the sodium chloride. So, aqueous sodium chloride, is there any kind of spontaneous reaction here? I have sodium chloride in solution? Nah. Sodium chloride's stable. I got sodium ions on here, I got chloride ions in here, water. But what I can do is I can put an electrode in here. I'll put an electrode in here. And then hook up some kind of power supply here. And then just crank up the voltage. If I crank up the voltage, I'm going to start stripping electrons off here, right? I got water present in here as well. Of course I want an inert electrode here. Let's use platinum or graphite or something. Platinum's fairly inert. Not totally inert. Did I talk about cisplatin? Cisplatin is an anti-cancer drug, anti-tumor drug. That has an interesting story behind its discovery. You know, the people were studying the impact of electric fields on the growth of cancer cells. You know, electric fields affect how the cancer cells grow and replicate. And so they put a couple of platinum electrodes here, turned up the voltage. When you turn up the voltage, you generate an electric field. You know, electric field is just positive on one side, negative on the other side. So you got this electric field. And 2 platinum electrodes in a, I guess it was in a petri dish with some tumor cells. And then just observe, you know, what was going to happen. Did they have some kind of hypothesis? Oh. Were they testing any kind of... No, this is just observation, right? See what happened. Well, what happened was this. The electrodes started reacting with whatever the medium was in here. And the product that generated from the electrode ended up killing all the cells. And so they thought, wow, whatever is forming at the electrodes is a powerful anti-tumor agent. It killed them. And to make a long story short, you know how they figured out? Because how do you isolate it? There's a whole bunch of junk in here. How do you figure out what is the active ingredient that's killing all the cells? And so that, you know, that goes back to Chem 1A. You know, how do you figure out that? Unknown. You'd have to do a lot of separations and isolate it. But you know, what quantities are we talking about? You did separations in qual, right? When you did separations in qual, you were starting off with what we call huge amounts of ion. You need huge amounts of ion because these separations aren't so clean. Well, you got a tiny amount of this chemical being generated with the electrode here. How do you separate it from everything else? without losing it entirely. So, you know what they did instead? Kind of interesting. They looked up every platinum compound in the book that they could find and then tested it to see if it had the same action. So maybe what they were forming is something that's been observed before. If so, and they found it. It was something that had been well known before. And so now it's a very common drug for the treatment of certain cancers. Anyway, getting back to this, what are we going to oxidize here? The species with the... Yeah, we're going to oxidize the species with the... highest oxidation potential. Asterisk. So we oxidize species with highest ox asterisk. Why asterisk? Well, I know that you're probably your mind's somewhere else. This is from yesterday. This is something I don't know. Maybe I didn't talk about this yesterday. You're right, I didn't. I ended up talking about chapter 19. I didn't get this far. The asterisk is because there's one exception. All right, the one exception is this. Chloride is easier to oxidize than water. But water has a higher oxidation potential. Why would that be? The reason is okay, chloride versus water. Water has a higher oxidation potential, meaning it's easier to oxidize. Should. And so when we look at it, when we oxidize water, that's going to cost us energy. When we oxidize chloride, that's going to cost us energy. When we oxidize chloride, it costs us more energy than water. This is thermodynamics. Remember, thermodynamics consists of a lot of state functions, right? Kinetics, we worry about what? The path. And so let's ignore thermodynamics right now and think about kinetics. In order to oxidize chloride to chlorine, all we have to do is pull an electron from the outermost shell. Is that difficult to do? No, an oxidizer comes along, plucks the electron off the outermost shell. In order to oxidize water to O2 gas, we got to break some bonds and form new bonds. Which one do you think is easier to accomplish? Which one do you think has a lower activation barrier? I'd say chloride. And so even though chloride costs you more energy, here, the activation barrier, this little hump, this hump is a little bit easier to deal with than trying to oxidize water, because when we try to oxidize water, it's going to cost us more energy initially, but we'll get more energy back than chloride. And so, in other words, and I think this is human nature too, because there's all these psychological studies. I was listening to the radio, and they were talking about what would you rather have? Would you rather have $5 today or $20 next year? Everybody said $5 today, right, or something. I don't know. It was something like that. Well, here's your $5 today rather than $20 next year, because this activation barrier is right, or 20 next year just seems forever from now. And so this activation barrier is kind of huge, and therefore chloride unusually is going to be the species that's oxidized because it has the highest oxidation potential. The oxidation potential of chloride is like minus 0.8 volts, and chlorine, of water is like minus 0.8 volts, and chloride is like minus 2 something, I don't know, volts. Chloride's pretty hard to oxidize. Are we going to oxidize sodium ions? What's the oxidation potential of sodium ions? No, oxidation. What is the oxidation potential of sodium ions? Give me as quantitative of an answer as you can give me. Less than. Less than fluoride, right? Less than minus 2.87 volts. That'd be less than minus 2.87 volts. That's about as quantitative as you can get. All right, over here. Okay, so over here, you know what's going to happen? Over here at this electrode, we're going to oxidize chloride to form chlorine. And so this electrode, we got this reaction occurring. Let me make some room here. We got the two chlorides going to chlorine and 2 electrons feeding into the power supply. And then over here, what's going to happen? Reduction. What are we going to reduce? The species with the highest reduction potential. Which species has the highest reduction potential? I'm not going to put up the chart because the projector is going to interfere. But you just look at your chart and see. We call this electrode what? On the right. Anode or cathode? Anode or cathode? Huh? Anode. This is the anode of the electrolytic cell. For the voltaic cell, that would be the cathode for the voltaic cell, but the cathode is not going to happen because this is so non-spontaneous. And so over here, we're going to reduce the species with the highest reduction potential, which is sodium ion. Sodium ion, does somebody have the chart in front of them? Water, which is water. And so when we reduce water, you get H2O liquid plus 2 electrons goes to H. Actually, I need to rebalance it. Let's do this. I think go 2 H2O liquids plus 2 electrons goes to H2 gas plus 2 hydroxides. And so over at this electrode, we're forming hydrogen gas. consuming 2 electrons. 2 electrons are coming in, and we're forming hydroxides. So it's a little messy, but can you see what's going on? No? There's a big problem, though. If hydrogen and chlorine gas mix, what's going to happen? What? Nothing? If hydrogen and chlorine gas mix, what's going to happen? Is chlorine a better oxidizer than oxygen or a worse oxidizer than oxygen? Chlorine's a better oxidizer than oxygen. What happens when hydrogen and oxygen mix? You got explosion. So you better have some kind of barrier that prevents the hydrogen being generated from mixing. This barrier can't go all the way down, otherwise we don't have electrical neutrality. And so this barrier has to go part way down so that any of the gases generated won't mix. Otherwise you're going to get an explosion. Perhaps. Alright, so at the cathode, cations would migrate, like the sodium ions. At the anode, the anions would migrate, like the hydroxide and the chloride. And so that's what we have here. So this was in one of the PowerPoint slides yesterday, and I thought I'd just write it on the board today. I want to make sodium metal. I don't want hydrogen gas. I want sodium metal. How could I do that? I have to make sure that there is no what around. In order to make sodium metal, I have to make sure that there is no water. One way to make sure there's no water is just melt the stuff. If I have molten sodium chloride, then all I have are sodium ions and chloride ions, and it's a liquid, so these are mobile. Now when I do this, I can figure it out. Actually, here I can calculate E of the cell. The E of the cell is going to come out negative. That means I have to supply a voltage greater than this to make it happen. This reaction doesn't want to happen spontaneously. I don't have my chart in here, but E naught of the cell is going to equal the reduction potential for water and the oxidation potential for chloride.
And we'll get that from the table.
You get that from the table.
Appendix D.
Either Appendix D or the table in Chapter 20. Either. So over here it's the same thing. You know, the chloride is going to form chlorine gas. But in this case, the only thing that we can reduce is sodium ion. When sodium ions reduce, does liquid sodium, because sodium metal has a very low melting point, and so does liquid sodium and sodium chloride mix? Liquid sodium metal and liquid sodium chloride, do they mix? Does oil and water mix? Why not? Because the difference in polarities. Is sodium chloride molten polar or non-polar? Polar. Is sodium metal polar or non-polar? Non-polar. So it's like oil and water. And sodium is less dense, so it floats to the surface. And so what we have here is we get a layer of liquid sodium on top of the molten sodium chloride. Now, what happens when liquid sodium comes in contact with chlorine gas? Explosion. And so you need to have a barrier here, otherwise you're going to get an explosion. Can't allow them to mix. We could figure out the voltage required, the voltage required by calculating the cell potential here. The cell potential is going to come out negative again, and this is just going to be the reduction potential for sodium ions plus the oxidation potential for chloride ions. We crank up the voltage. We can electrolyze water too. Let's say I have nothing in here except just pure water. If I just pure water in here and then I crank up the voltage, what am I going to form? Hydrogen gas and oxygen gas. So that's electrolysis of water. We'll strip electrons off water and we'll force electrons onto water. And when we look at water, H2O, the hydrogens will want the electrons and the oxygens will give up the electrons, looking at the oxidation state. So hydrogens take on electrons, we form H2 gas. If oxygen oxide, O2 minus, gives up electrons, we form O2 gas. So hydrogen and oxygen. That's with water. You usually put some acid in there to help electrolysis. Okay, now we're going to do it in a special apparatus here. What electrode should go over here? What terminal should go on the power? The red or the black? On the right side. What do I want to put? The red or the black? I'm going to put the red. It's going to be red. Over here, just a wire. I'm going to put graphite here. My electrode. So here. This is the setup here. So I got this U tube, and I have some graphite electrode here. I have my power supply here. It's heavy. But I have no red wire.
Stock room.
Stock room. Well, while I get that, I want you to tell me what's going to happen here. So I got this U2, and you know what I'm going to put in here?
Water.
Not water. Potassium iodide. Potassium iodide is generally regarded as safe, so I'm not going to do the goggles. Although, yeah, I better do the goggles. That's the proper example. So I got the two electrodes here. Hopefully they're clean. And then I'll pour some potassium iodide in here. Just Ki solution. So we'll just do a little electrolysis. I have the electrolysis of water we can do anytime. So this power supply is extremely heavy. This one is a fancy one because not only can we control the voltage, but we can also control the current. Slow down the current, speed up the current. And so that's why this one This one's like $1,000 power supply. Just the simple ones would do the voltage, aren't that expensive. So I'll go get a wire, but you tell me what's going to happen here. You know, I'm going to collect the black lead over here. Unless other wires back here? So what do I have in solution over here? I have potassium ions, iodide ions, and water. You might not need the table. I don't think you need the table to tell me what's going to happen. I think you can figure it out. So I'm going to connect the red wire to the red terminal here. I'll attach it here. So what's the power supply trying to do to the red here? It's trying to pull electrons or give electrons. Yeah. Make sure I'm not touching this metal here. And then the black goes here. Okay. And then what's going to happen at this electrode? Is this the anode or the cathode? That's the anode. Oxidation is going to happen. So what are we going to oxidize? Iodide. You know, iodide's a big ion. It should be easy to oxidize. In fact, it is fairly easy to oxidize iodide. And so you're supposed to store it in a brown bottle so it doesn't get hit by light. Over here it might be a little trickier, but it's still, I don't think, is any problem. What are we going to reduce over at the cathode? Water. Just think, because if we reduce potassium ions, we'd form potassium, metal, and water. Is potassium, metal, and water a stable combination? No. It leads to large explosive reactions. And so let's turn this on and watch. Turn up the voltage. Here we go. I'm doing pretty high voltage, 13 volts got here. I get shocked. Oh, you know what? There's some phenolphthalein in here too. There's phenolphthalein. Yeah. Well, I'm going to shake this electrode. Do you see? You see that pink color? I'll do it again. Over at this electrode's starting to turn, there's some
Yellow, right?
yellow, right? Do you see that? It's hard to see. It's starting to turn yellow. I'm going to crank up the voltage even more. I got to watch out because if the voltage gets too high, do you know what happens? An arc. You know, it's high enough to ionize air. And I don't want that. I don't want a little lightning bolt drop. The air, I don't have to worry because I need to get to about 5,000.
You're 17.
17. 17 volts. I haven't had a bad experience, you know. Have you ever touched the tip of your tongue to a 9-volt battery? Yeah. Just that. Also, you know, 120 volts is a bit much too. All right, do you see clearly what's happening over here? Do you see gas bubbles forming? There are gas bubbles forming.
I see.
And do you see it's turning pink? That means we're forming hydrogen and hydroxide. Over here, it's turning brown. But pretty soon, if it gets concentrated enough, it looks purple. You know, right off the electrode, purple plumes are coming off that. Do you know what those purple plumes are? Iodine. I2 is purple. And as it gets diluted, it looks brown. So were you right in your predictions? Huh? Yes? Did you predict that's going to happen? Yeah, I mean, iodine is fairly reactive chemical, and of course hydrogen gas is fairly reactive here that we're producing over at this electrode. And so we have the electrolysis of potassium iodide. All right, that's it for chapter 20. So we're going to have our test on chapter 20 next week on Thursday. Next week we're going to do chapter 24 and start 25. I was hoping to start 24 today, but I think I won't. All right, I'll let this go if you want to take a look at it. And you can take a break. Let's take a break and then we'll start. Yeah, turn in, you know that extra credit thing? Turn it in if you'd like. Yes, in the homework.
Did you want something if we couldn't go to that?
Yeah, I'll talk.
Okay.
Think about it.
Let's go.